Hey everyone, welcome to the lecture by me that calls microstate geometries.
Thank you. Looks like we're getting down to the hard core now. So, okay. So let me remind you what we were doing. I was talking about this action, which is in 5-dimensional supergravity. In fact, n equals 2 supergravity. And it contains a graviton, 3 vector fields, and 2 scalars. Two scalars because they satisfy that constraint. And last time I talked about the fact that you couldn't get solitons in this thing without topology, and I talked about why that was. And so the goal today is actually to go through the construction, in fact, supersymmetric solitons. If you can make a non-supersymmetric soliton, I'll buy you a very nice bottle of wine. Supersymmetric solitons. There's a few known in the literature, actually, so that's not quite true, but that's the goal for today. And then the last lecture will be about basically the interesting ones and then some of their properties. So that's my task. As I say, we have to work with this action, but in fact, of course, since we're looking for supersymmetries, there are gravitini in this theory. There are 2 of them. And so we have to solve these equations in much the same way as we did before, but also, because it's coupled to vector multiplets, there are also some spin half particles, delta psi, which are basically, let me just call them A for the moment, also set to 0. I'm not going to go through that because we could spend a lecture just in the mud. What I'm going to do is tell you what the answer is and what the so-called Dps equations are, and then give you a sense of where they come from. But the basic idea is very much like the discussion I had in the first lecture. So to get to the Dps equations of this system, what you do, first of all, is you know that the thing is, the metric must be time independent. In fact, the metric must be stationary, because if it's Bps, there must be a time-like killing vector. So therefore, you can write the metric in the most general stationary form. There's some function that can multiply the dt squared. There is some one-form field. And then I'm going to, just for convenience, put the same factor of z here in front of a 4-dimensional metric. And this will be henceforth called the base B of the manifold. This can be any one form on B. And moreover, Z is just some function on B. Everything is time independent. So everything, so I'll call these coordinates up here typically some kind of coordinates x. And everything depends on x in principle. But that's the first thing that supersymmetry tells you, that there's a time-like killing vector, and therefore the metric can be written like that. Oops, eraser. Oh, there we go. Let's keep that for the moment, I think. The other thing we're going to do is, of course, decompose the Maxwell fields in a very similar way. So basically, the Maxwell fields in this theory, things that underpin this, decompose in exactly the same way. You can have a component parallel to the time direction, and we'll just call that zi to the -1. Those are the electrostatic potentials, and then there can be Maxwell fields or one forms on B. And by way of notation, we'll define theta I to be the exterior derivative of these BI's. So you should think of this as basically the electric potentials, and this is the magnetic stuff. So the fact you get a time-like killing vector means you unambiguously can decompose the metric into a sort of spatial base, a time direction, and similarly you can decompose the Maxwell fields into electrostatic potentials and magnetic fields, and these will play a huge role in what we're talking about. These are the magnetic fluxes on magnetic fluxes. solution. Okay. Looking puzzled, Marco. Good. Right, so now the BPS equations. Basically, once you've decomposed them like this, let me tell you what those equations you have to satisfy are. And we're going to make lots of comments about these equations. First and foremost, 1. Theta i's must be equal to the dual of theta i's, where whenever I write star in this context, that means in the 4-dimensional base. So it's an ordinary good old-fashioned Euclidean star. They have to be self-dual, and I'll explain how this comes about very heuristically. The second thing you have to satisfy is that the Laplacian on the zi's has to be equal to, up to factors of 2, I think there's a half in here, Cijk theta I, theta j, wedge theta k with a dual. I'll say more. I'm going to say a lot more about this in due course. 3, the last part of this is that the one-form field, let me remind you what the metric looks like, ds5 squared is equal to minus z to the minus 2 dt plus k. This k, this one-form field, plus z ds4 squared. dk plus its dual must be equal to zi theta I. And so my first task is basically to give you a sense of where these come from. So basically, what are the issues here? Oh, and one other very important equation, which I haven't stated. We have, as function z, and a bunch of electrostatic potentials. Part of being supersymmetric, or BPS, is that the mass must be locked onto the charge, which means that the coefficient of the metric here must be related to the things that determine the charges here. And it happens in exactly the way one might expect. 2 and Z3, with 3 electrostatic potentials multiplied together, third power, so the geometric mean of the electrostatic potentials. So that's the, and I'll say more about this in a minute. That's the sort of M equals Q condition. So the calculations to get to these equations is rather a lot more involved than what I did in the first lecture. As I said, would take a whole lecture to just dissect these BPS equations. And I don't think that's a good use of time. So let me sort of explain where it comes from. Let's get rid of this. So everything really interesting that's happening happens on this base B, this 4-dimensional spatial slice.
Sorry, Nick.
Sure, yeah, please.
In the first equation, on the right-hand side, it's theta I.
Sorry, yes. Same index. Oops.
I mean, the end of
Yep. It's the same theta.
Okay.
Each of them has to be separately self-dual. Okay, so all the interesting things happen in this base B. So remember, this the metric we're dealing with. And basically, we'll be talking a lot more about this. And then once you've got B, everything else goes along for the ride. So this is where base B. Any other questions before I proceed? Okay, so where does it come from? So when you start analyzing the SUSY, basically you start getting equations like this. You find that each of the thetas times the gamma matrix on epsilon has to be 0. This is one of the constraints you get. This is when it's a rather complicated story, but you basically have to decompose this and the variation of the lambdas being 0. And you get this kind of condition on the spinors. You also find another condition implicitly, and I'll say more about that in a minute. Where this is the Riemann tensor of the 4-dimensional base. Riemann on B. So that immediately tells you something very useful. How do you satisfy this thing? Well, it turns out the only way you can satisfy it non-trivially in this context is if the following is true. You want basically a theta and two gamma matrices to kill your epsilon. So if you think a little bit about it for a moment, you say, okay, suppose I had gamma AB of epsilon, let me write it explicitly, gamma A, gamma B of epsilon is equal to 1/2 epsilon AB, where this is the epsilon symbol on the base, gamma C, gamma D on epsilon, and I'm going to get a sign wrong unless I check my notes. Get there. Okay, where'd it go? Lost you. That is a sign. It's, yes, that's the right one with the minus sign. Okay, if you have this, all that is equivalent to, so it says things like gamma 1, gamma 2 acting on epsilon is equal to get minus gamma 3, gamma 4 acting on epsilon, things like that. Well, it implies that and all the other permutations on the theme, but multiply both sides by gamma 1, 2, 3, and you see that this original thing is entirely equivalent to 1, 2, 3, 4 on epsilon is equal to epsilon. I should write it out. I'm using the common shorthand. Okay. So remember I said that supersymmetry always involves, well, almost always involves a projection condition. This is the projection condition you have to impose. It's almost, but not quite, equivalent to gamma naught of epsilon is equal to epsilon. There's a technical point about five-dimensional supergravity that there's a symplectic Majorana condition. I don't want to go there. It's almost, so let me leave that there. This is the projection condition. Gamma 1, 2, 3, 4, if you square it, squares to 1, and it's traceless. It's traceless. So therefore, just as before, it has eigenvalues plus or minus 1, and it has equal numbers of plus 1s and minus 1s. So exactly as before, this projection condition cuts the supersymmetry in half. So gives you halves the supersymmetries. So it moves what the theory started with 8 supersymmetries, and it's now got 4. So that's the only projection condition there is. And now the important point is when you look at requiring this or this, you see that implicitly the gamma AB epsilon must be equal to its dual. And so this, having this condition on the thing, having this being 0, let me come back to this one, means that basically for this to be 0, if you have theta AB I equal to 1/2 epsilon AB CD theta I CD, then this condition plus this condition implies that. So in other words, supersymmetry tells you you've got to have this. The way you get it is you impose this projection condition on the spinner, which gives you this identity. You put that identity in here, and you get this plus its dual acting on epsilon as epsilon. So the way you satisfy it is then by requiring that. So the self-duality of theta is imposed on you by supersymmetry, and it comes about by imposing this projection condition. Let me be very explicit. Maybe that's a better way of doing it. So if I take, you want to have this condition. Oops, let's get rid of it. Theta I. Yes, let me get rid of it. You want this to be 0, but you know that epsilon satisfies this condition here, so you can write this as 1/2 of theta I AB gamma A gamma B plus minus the dual of theta I AB or CD AB, yeah, CD epsilon, sorry, gamma C, gamma D. Actually, let me write it all the way out. Epsilon A, B, C, D, gamma C, gamma D of epsilon is equal to 0. And so basically what happens is, all I've used is this projection condition on epsilon. I just said gamma AB is equal to get the epsilon times gamma CD, and I'm missing the theta. So I'll put the theta there. I'm good. All I've used is this fact, and then basically what happens is you then have to learn that this fact, then this contraction here has to be 0, which gives you that condition. So the first condition of self-duality of theta comes straight from supersymmetry. Okay, now the next condition, Dps equation 2. That, remember what I said the first lecture? That's a second order equation. That is an equation of motion. And so you have to impose, or sometimes you have to impose at least one equation of motion. And it's easiest done from the Maxwell equation, e.g. the Maxwell equation. And equation 2 is part of the Maxwell equation. It's simply the electrostatic part of the Maxwell equation. It comes from the statement that d of f, or d star of f, is equal to f wedge f. If you take the electric component, remember A is morally z to the minus 1 dt. If you take the electric components, then this gives you essentially the Laplacian on z's, zi's. And then the right-hand side is the Maxwell component, but that's just the fluxes. So basically, the second equation is simply porting part of the Maxwell equation straight into this. And the last equation is again SUSY. It's not so easy to see how it comes about, but basically, anything in here that's a first order equation is supersymmetric, and anything that's a second order equation is actually an equation of motion. So, and the last gasp of this is, if you remember the first lecture also, we had to finally solve the Killing spinor equation, and the Killing spinor equation involves delta sine mu is equal to grad mu of epsilon plus a lot of stuff. And you want to solve that to equal to 0. What that then boils down to, once you've satisfied all these equations, is that I'll call it grad alpha hat on epsilon is equal to 0, where this is the covariant derivative on B. B. Okay? But remember also you have this self-duality condition that gamma AB minus 1/2 epsilon AB CD gamma CD of epsilon is 0. Now what you can do is you look at the integrability condition of this equation. We leave that there. I'd like to keep this, but let me leave that there because I'm going to talk all about the physics of what's buried in this equation in a minute. So you look at the integrability condition of that equation, alpha grad hat beta commutator action on epsilon is equal to 0. This becomes 1/4 the Riemann tensor AB on the 4-dimensional base, gamma A, gamma B of epsilon is equal to 0. And remember we solved the other condition, theta AB of epsilon, gamma AB, gamma B of epsilon is equal to 0. This is what was required to solve that condition. And so to solve this, it's exactly the same story. You have to require R mu AB is equal to 1/2 epsilon AB CD R mu CD on the 4-dimensional base. I'm going to talk all about what that means in a minute. Okay, questions or comments? Yeah.
Sorry, just for notation, in 2, the covariant derivative is in 5 or? 4. 4. And the other stars are also?
Everything is in 4, sorry, yes, thank you. Everything interesting happens. In fact, most particularly what you're supposed to take away from this is that we are now down, all the equations are in the 4-dimensional Euclidean base, or 4-dimensional base, I should say. I'm going to say a lot more about that in a minute. So, what we have here to add to this is, let me write down the supersymmetry conditions, and we're going to dissect them all in what they mean. So the 1/3, That was the warp factor. And then this guy. 1/2 epsilon A, B, C, D, R mu nu. C, D. Okay. And okay, we'll leave it like that. Right. So that's what we get. So let's talk about what it means physically. First and foremost, let's just remember where everything is in the Maxwell field, the basic Maxwell field and the basic metric. The metric is here. ds squared is equal to minus z to the minus 2 dt plus k squared plus z ds4 squared. And the AIs, the electric fields, decompose into minus zi to the minus 1 plus k plus b, and db I is theta I. Okay, so let's look at what's happening here. The first thing you should notice, the BPS equations are a thing of great beauty. The first of which is A, they are linear. What do I mean by that? Well, the first one's obviously a linear equation for theta. The second equation is also linear in the sense of the equation you have to solve is a linear equation sourced by the solution of the previous equation. So, yes, it's nonlinear in the sense of the sources are all nonlinear, but the actual equation you have to solve is linear with sources, which are complicated. This was not guaranteed. In fact, when these BPS equations were first analyzed, I think it was Gauntlet and Gutowski, they unpacked them, but they didn't realize they were linear because they didn't reorganize them the way I have. If you reorganize them in this way, you realize that they're a linear system. Every step of the way, you solve the first equation, you use the solution to that as the source of the second equation. This is a linear equation. You use the previous two solutions to source the third equation, which is a linear equation. It's not just linear, it's 4D Euclidean electromagnetism. So in other words, solving this system is actually 19th century mathematics. It's not, except for a few little wrinkles we're going to run into. So that's the first thing you should note about this thing. Okay. Let's see, linear. Right, middle BPS equation, excuse me, the middle BPS equation, B. The middle BPS equation, basically the Laplacian of Zi is equal to minus star theta j wedge theta k with appropriate structure constants, Ci, j, k. Look at the structure of it. Remember, this is the electrostatic potential. And these are two magnetic fluxes. So this is what I was promising before. It expresses the fact that the electric field, d star f, proportional to f wedge f, that's where it comes from. But it tells you the electric fields here are sourced explicitly by magnetic fluxes. Okay, third point. So the last equation is also extremely interesting in terms of its physical structure. Look at what K is. K dictates the angular momentum of the solution. It's the mixing of space and time. And if you go back to my, I guess, the second lecture, you'll see that if you want to pull out the angular momentum metric, this is the guy. And in fact, K is sometimes called the angular momentum vector. It encodes all that information. It tells you how it's rotating. And look at its source. It says that it's sourced by Zi theta I. And think about what these sources are. Remember, this is electric, and this is magnetic. And so morally, this thing is like an good old-fashioned E cross B term in electromagnetism. And so the angular momentum of this system is derived from an interaction between the electric fields, where's it gone? here and the magnetic field's there. And so it's exactly, this solution generates angular momentum in exactly the way that you would get with a monopole in the presence of an electron. It's an E cross B interaction that is creating the non-trivial stuff here. Okay, any questions at this point? Any issues? Let's cut that. Issues, concerns? Okay, next thing, monodromy. So what I want to do is get to what's underpinning this. I think I can get rid of this. This constraint, what does this mean? Oh, okay. Come back to that. I'm going to keep the thing on the bottom. Yeah, that's what I want. That guy. Okay, so now, next thing, monodromy on B. Okay, so in GR, hopefully you learned about parallel transport round closed loops, sometimes called the monodromy of a metric. We're in 4 Euclidean dimensions. Closed loops in B. Okay? If you parallel transport a vector around a closed loop, it preserves the norm, because parallel transport preserves the norms of vectors, but it can rotate. So this produces a rotation, which is an SO4 rotation in general. And I ask you to remember that SO4 is at least locally the same as SU2 cross SU2. Now, depending on how you write the indices, it's actually usually written the other way around. R mu nu AB, this is the, actually let's write it like this, is the rotation matrix. And then this is, if you wedge it with dx mu, wedge dx nu, then this is the area element of the loop. So what I've done is I've reversed the indices here, so I bracketed it this way around. It's using the symmetries of Riemann. You can flip it around. So what I'm observing here is that this is a constraint on these rotation matrices. And in particular, what it says is the base metric must have self-dual matrices, rotation matrices. That's what this equation says for any closed loop you make. If it's self-dual, that means the monodromy can only be one of the 2 SU2 factors. Let me just say, let's call it left and right. In other words, the monodromy is that, and the curvature in SU2 right is trivial. So in other words, on a manifold in 4 dimensions that's Euclidean, the monodromy group is SU2 cross SU2, and there are a species of metrics that are sometimes called half-flat metrics. Where a half-flat metric is defined to be one where only one of the SU2 says non-trivial monodromy, and the other one has trivial monodromy. So in other words, this constraint is telling you better use a half-flat metric, but that is the same as calling the metric hyperkähler. I won't say why it's called hyperkähler, we'll just use some basic facts about hyperkähler manifolds. So, in other words, the metric has to have a rather simple monodromy group, and it turns out that's hyperkähler. So, we learn from this that the base is hyperkähler. Right. What's next? More things from the supersymmetry conditions. Oh, let's leave that there. Right. So let me summarize what we have to do. We have AI is equal to minus zi to the minus 1 dt plus k. plus bi. Theta I is equal to bi. The base metric, ds4 squared, must be hyperkähler. And we're going to look at a very simple family of hyperkähler manifolds. Kähler. Okay, that metric must be hyperkähler. We also must put Z as the geometric mean of the three electrostatic potentials. I'll say more about that in a second. And then we solve the BPS system. Theta is equal to star theta, I, this is 4, and then 2 is del squared Zi. And let me write it schematically, star theta, wedge theta, and then 3 dk plus star dk is equal to Zi theta I. A couple more observations about this system. I think I'm up to about D. Look at this equation. I should have mentioned this right at the beginning. Remember, theta is equal to dB, so d theta is 0. Is equal to 0. But it's self-dual, so therefore d star theta I is equal to 0. That means that theta has got to be cohomological. It's harmonic, if it's going to be smooth, that is. It satisfies d theta is 0 and d star theta is 0. And the last thing I want to observe is that this condition here, Z is equal to Z1, Z2, Z3 to the third. If you look at what it says, I mentioned this in passing, but let me really spell it out. Z is the coefficient of dt squared. And if you go back to my last lecture, the coefficient of dt squared is what you use to read off the mass. So this equation, if you're doing expansion infinity, you get a statement about what the mass is. But the Zi's are the electrostatic potentials. In fact, the Zi's typically go like 1 plus qi over r. Or rho, actually r squared, or rho squared, distance squared. And so when you do this expansion, all the ones typically talk to each other, and this turns into m is q1 plus q2 plus q3. So this last constraint is the mass equals the charge. In this particular case, the mass is just the sum of the three charges. So it really is honest to goodness BPS.
Everything becomes some expansion, right? Is the leading order term, or is this an exact result?
It's an exact result. What you do is you look at the leading 1 over r squared terms of infinity, and in G0, it's the mass, and in the electrostatic potential, no, that's good. And I've got all these ones in here to get rid of the, so you get one time, you get ones from everywhere else, and then you get Q1. Yep. Okay, I think I'm basically done about that. I think I've got everything I wanted to say. I want to just make a sort of a warning, and then we'll move on. So our task is to do the following. Everything rests on the base metric. So the first thing we do is we choose a hyperkähler base metric. On this hyperkähler base metric, we find harmonic forms, harmonic magnetic fields satisfying this. We then take those harmonic magnetic fields and compute the sources, and that gives us the electric fields. And then having given the electric fields and the magnetic fields, we put them in here, and we solve for the angular momentum tensor, and we've got our solution. It is nothing more than Euclidean electromagnetism in 4 dimensions. And the last little gasp of this discussion is to note how the old story fits into this current story. If you have no magnetic fluxes, if theta I is a 0, if you decide I don't want the magnetic fields, look what happens. The BPS equations boil down to del squared of Zi equals 0, and dk plus star dk is equal to 0. This is the multi-centered black hole in 5 dimensions. It's the 5-dimensional analog of the thing I did in the first lecture. You have harmonic Zi's with singular sources, And in fact, you have a harmonic K. The new element here is that things that are BPS in 5 dimensions can actually have non-trivial rotation, but everything here has to have a singular source. The only way you can avoid having singular sources is to have non-trivial cohomology. As we said, the only way you can avoid having this set of equations is to have these, and these have to be self-dual, and they have to be smooth. You have to be, theta must be cohomological. And that's how the theorem I talked about last time comes out extremely explicitly when you actually analyze the BPS equations. Okay, so what we're going to do is set about solving these, but I just want to point out there's a huge danger which we got. So this whole program, microstate geometry program, dodged many, many, many bullets. And there's another bullet I'm going to allude to. What we want is, of course, more chalk. No, see, I think I'm running low, but okay.
I'll go.
Yeah. Let's see. So what we want is a solution that is asymptotic to R41, asymptotic to flat space. If you make it asymptotic to something else, then you have to change there are more complicated theorems. But I want to just say, let's make it asymptotic to R41. That means that B, the base, is asymptotic to R4. And you run into a very simple theorem that's attributed to Hitchin, but it's actually fairly simple to prove. Remember, the base metric must be hyperkähler. And you can ask the question, what are the base metrics that are smooth, hyperkähler, Riemannian, and asymptotic to R4? And the answer is theorem only R4 itself, which means there's no cohomology, which means you can't find any cohomological thetas. It looks like you're dead in the water. We're not going to be dead in the water. We're going to proceed with this, and for the moment, not worry about making the solution asymptotic to R41. We'll just look at some hyperkähler metrics, and then we'll see some magic that we can do, which looks outrageous at first, but once again makes the microstate geometry program survive yet another serious challenge. Okay, so our task is to start with nice hyperkähler metrics. We've got to start with some geometry, and then we start loading it up with electromagnetic fields. That's our task. So we're going to start off with hyperkähler metrics. And in particular, I'm going to talk about what are called Gibbons-Hawking metrics, sometimes called ALE metrics, but that's not good enough because the metrics I'm going to think about are much more general, but they fall into this Gibbons-Hawking form. So, independent of whether you care about microstate geometries, Gibbons-Hawking metrics are something everybody who does geometry should know about. They are the most beautiful, explicit, sort of simple thing that you can analyze that have non-trivial topology and non-trivial holonomy and so forth. I often joke that they're the simple harmonic oscillator of geometry. They really are. So we're going to talk about these and come back to this problem. So I'm going to unpack this for you by just doing a bunch of explicit examples. And then we're going to use them. Any questions though before I go there? Asymptotically locally Euclidean. That will come out later. Remember I said it's asymptotic to R4. It's not going to be asymptotic to R4. It's going to be asymptotic to R4 modded by a discrete group. That's asymptotically Euclidean, locally Euclidean. Okay, ALF is asymptotically locally flat, and ALG is some joke. There is a thing called ALG. It's asymptotic to R2 cross S2, I think. Anyway. Right. Well, yes, Gibbons-Hawking metrics. So I'm going to look at them. So what I'm thinking about is the base manifold that we're messing with. It's a 4-manifold, B. And I'm interested in some interesting hyperkähler geometry on it. So I'm going to just claim the following is an interesting piece of hyperkähler geometry. There is going to be a fiber, a function V, and then V, and then what makes it so beautifully simple is that it's basically a warp form of R3. Flat R3. V is a function of Y, And A, we'll talk about in a minute, is a vector field. A is equal to A, vector A of y dotted into dy. And we're going to talk about the constraints. So this is a circle fibration. This is a circle psi. And we normally periodically identify it to have a period of 4 pi. It turns out to be the natural units, and you'll see in the notes why it is. But at the moment, a priori, without saying anything about v, you notice you can rescale y's, you can rescale v, you can rescale v to -1. The period of psi can be taken to be anything you like, but I want to fix some of the rescalings by saying I'm going to take psi to have a period of 4 pi. It turns out to be the natural one, but you can pick it to be anything you like. Yeah.
Is that hard because I thought it was fixed by smoothness and
Oh. Okay, smooth, but ultimately, by choosing this, my smoothness conditions will become integer coefficients, integer conditions on these things.
do you allow conical defects?
Oh yes, absolutely. So, but I wanted to just say, one way or another, I'm going to pick that period right from the get-go, and then everything will come out with integer normalization. If you don't do this, you'll start getting, if you do it with an r psi, everything will come out with integers times r psi. So, yeah.
Did you get something that was asymptotic to R4?
I'm getting there. I haven't said yes, I wanted asymptotic, well, we'll get to that. Now, what are the conditions? The conditions are del squared of v. Now, this is always, in this context, going to be the three-dimensional Laplacian. So let me call it the Laplacian on y, if you like, of v is 0. And then the curl of A, the gradient of v must be equal to plus the curl of A. And so this is the integrability condition for this equation.
Sorry?
Yeah.
The Laplace for the flat metric?
This is the Laplacian of the R3 metric.
Okay.
And this is the gradient in the R3. So everything here, when I write a differential operator, is going to be in the R3. Everything is going to be assumed to be independent of psi. So I'll say, dd psi is a killing vector. Sorry, Monica, you had a question?
Yeah, sorry, I just didn't follow. So what equations are you solving? What is it?
I'm going to, if you impose this, my goal is to make it hyperkähler. So if you impose this, this makes it Ricci flat. Flat, and in fact hyperkähler. So, exercise. I put this in the notes. Calculate the Riemann tensor of this metric and show that it satisfies the appropriate self-duality condition, provided these conditions are satisfied.
So what you're solving is self-duality of Riemann?
A Riemann of a four-dimensional Riemann tensor, R nu AB is equal to 1/2 epsilon AB CD R mu CD. I claim if you want to have that with this ansatz, you've got to have that. No. It is the most general solution where this killing vector is actually going to preserve all the hyperkähler structure. I didn't want to get into that level of technicality, but the broader point is this is the most beautiful computable set of hyperkähler metrics. There are more general hyperkähler metrics like the Hitchin metric, which are much more complicated, and there are also ALG submetrics. There are all sorts of weird metrics. But if you want this dd psi, if you want the killing vector to preserve your hyperkähler structure without charges, then this is the only metric.
It's been a while since I haven't done hyperkähler, so you start with flat space and then you can write some
Flat R3?
flat R4, I thought.
Okay, well,
It has to be even dimensional, right?
hyperkähler has to be multiples of 4.
Right. Okay, so you start from R4. and
I'm not starting from R4, I'm starting from, okay.
What do you mean by preserving the hyperkähler?
I haven't even exhibited yet. For the moment, okay. For the students here, I try to keep it simple. I've got a metric which is really simple. There's one potential function and a non-trivial vibration. And I claim it satisfies the condition we want to solve all these equations. It satisfies this, and if you write this down, homework exercise, show that this guarantees this. We'll get to the final structure in a minute.
What I don't understand is what does this condition have to do with the hyperkähler?
Okay, this is a restriction on the monodromy. This says the monodromy is not SO4, but it says it only has SU2 monodromy. And that's hyperkähler. Okay, hyperkähler says that. Sorry? Oh, monodromy, sorry, yeah, holonomy, monodromy, yeah, sorry. Monodromy of the parallel transports, yeah, holonomy, thank you. Holonomy. It's got SU2 holonomy. It's a complex manifold, that tells you it's SU2 cross U1. It's Ricci flat, that tells you it's SU2.
I see. And so since I didn't
No,
follow-
no, go for it.
So was it your supersymmetric condition that told you that this baseline?
Yes, absolutely.
And now you're trying to look for some sort of general hyperkähler manifold?
I've got a shopping list. I find a hyperkähler manifold. I then have to solve a sequence of electromagnetic equations on that manifold. But the starting point is I've got to start with a hyperkähler manifold. And so the simplest claim I'm going to make is this is a nice, very nice set of hyperkähler manifolds, which is really simple to analyze, so we're going to work with these. There's a question about whether it's the most general one, and the answer is absolutely not.
The
But
most general one having a holonomy?
no, the SU2 holonomy is hyperkähler. There are lots of manifolds with SU2 holonomy. No, that's fine. If you get the question, I bet you half the class does. So the point is, it's got SU2 holonomy, or holonomy, thank you. But there are other metrics that have that. This is special in that this killing vector is present, first of all, and that it preserves the three complex structures. That's, if you ask for the most general triholomorphic killing thing with a triholomorphic killing vector, this is it. Done. But I'm not looking for generality, I'm looking for examples.
I'm asking the same question again because I got confused. So you have some supersymmetry equations.
Yep.
And in particular, you need to solve for some base manifold.
Yep.
Which have to be hyperkähler by supersymmetry.
Yes.
Is the hyperkähler condition the same as the self-duality, or it's implied by self-duality?
It's exactly the same as self-duality in 4 dimensions only.
In 4 dimensions. Okay, fine. So the hyperkähler is the same as self-duality of the Riemann
Yes.
tensor, and now you're just exhibiting some particularly nice set of solutions.
Exactly. That's exactly what I'm doing.
And then the self-duality of the Riemann tensor, well, in particular, I guess it implies that the Ricci is 0.
Yes.
Or
It does.
maybe
It does.
ansatz, and then you solve self-duality.
It does.
You find that V has to satisfy those equations.
Sorry?
That the function V and the function A
Have to be exactly. So this is the nicest, the beautiful thing about the given talking metrics is they are the simplest class of hyperkähler manifolds that are highly non-trivial and have all sorts of cool structure that you can see extremely explicitly. So that's why they're here. Uniqueness issues are another question. But the holonomy issue of the Riemann tensor is what pushes you straight down to this thing. So if you put it another way, since you only got to give you an idea where the hyperkählarity comes, if you've got an SU2 holonomy, it means that the tangent bundle breaks into the tangent bundle two forms break into the self-dual ones and the anti-self-dual ones. The connection is trivial on the anti-self-dual ones because the Riemann tensor is self-dual, or vice versa. I can't remember which way it goes. But anyway, the bundle is flat on the anti-self-dual forms. Therefore, those three anti-self-dual forms can be made covariant constant, and those are the hyperkähler forms. So that's explicitly why this condition tells you it's hyperkähler. It tells you that the two forms are flat when they're anti-self-dual. Okay, we got.
Can I play the same game in the compact case?
This is, yeah, absolutely.
So what do I get then? Some K3 also?
Yeah, so ALE is in fact typically considered a local model for K3. So K3, if you zoom in and decompactify, is ALE. That's one of the other cool things about it. It's a local model.
So I can also write it in this given solver.
Oh no, K3 you can't because K3 is compact.
Yeah, this is a question.
You can't. You're local, but if you zoom in, this is a quote local model of it, where you ignore all curvature effects that go when you go further out. You go flat rather than curling around and closing the manifold. So zooming in on a piece of substructure, ALE, or these metrics are in fact local models of K3. Okay, wow. Right, so let me talk about my choices here. 10 minutes, okay. So we do the stupidest, obvious thing that you can do. As I say, it really is unbelievably simple, like the harmonic oscillator. So we've got to solve this equation. So what do? We take V, is equal to the sum of charge points with some charges, little qj over rj, where rj is defined to be equal to the magnitude of y minus some yj, like this. So in other words, we have our R3, and over the surface of them we sprinkle some points, typically now called Gibbons-Hawking points. These are the points yj where we're going to allow sources for V to occur. And then you have to solve del cross V, del cross A is equal to the gradient of V, and that's an elementary electromagnetic exercise. If you put it on the, if you put the z-axis, if you put the, let's see, the Gibbons-Hawking point, suppose Rj is equal to y1 squared minus plus y2 squared plus y3 squared, y3 minus a squared to the half, then it's elementary to check that A for that guy is equal to y3 minus a over Rj plus a constant times d phi, where phi is the axis. So this is rho and this is z. Let's see, rho e to the I phi. So phi is basically the azimuthal angle around this axis. It's an elementary exercise to solve. I won't go there. But basically, you now take V's to look like this. You can add a constant. That makes Taub nut generalizations. I'm not going to go there. I'm just going to keep it simple. I'm just going to take V to be purely a bunch of three-dimensional electric charges. Adding constants changes the topology in an interesting way, but we're not going to do that. We don't have time. Okay. So there's our metric. Now it looks bad because we made V blow up at a bunch of points, so this looks kind of singular. So now we have to dissect what actually happens at apparently singular points. And I claim the metric is smooth up to orbifold points. So, and I remember my period psi is equal to psi plus 4 pi. So I want to examine what happens as Rj goes to 0. And what I'm going to do is I've got this Gibbons-Hawking point, which I'm zooming in on, and I'm just going to erect some nice, let's see, polar coordinates, I think is what I want. Yes. So I'm going to erect some polar coordinates at this point. There's going to be an r hat, there's going to be a theta hat, and a azimuthal angle phi hat. So r hat, theta hat, and phi hat are polar coordinates at yj. Okay, so now, as I do that, it's relatively easy to show that A, if you take its form, is simply cosine theta hat d phi hat. You can ignore the constant for now. And so if you write down what this metric is zooming in, V of course is going like 1 over, qj over r hat. And so when you write down this metric as you limit to this point, this becomes r hat over qj d psi plus a squared, or d psi plus cosine theta hat d phi hat all squared. And now here you get plus 1 over r hat. And now we'll write flat metric in the polar coordinates. Qj d r hat squared plus r hat squared d theta hat squared plus r hat squared sine squared theta hat d phi hat squared. Okay, so now my task is to, this is what the metric becomes as you approach this point. Well, this term looks fine. The problem is here. It looks like this qj hat is blowing up. But in fact, it isn't. It's just a square root branch cut singularity. So let's pull it apart and see what's there. So let's take this limit in metric. It goes to, I'm going to make a change of variable. I'm going to write, which way does it go? R hat is equal to 1/4 rho squared. And the whole point is dr hat is equal to 1/2 rho d rho. And when you compute this, all the rho squareds cancel and go away, and you see that the metric becomes d rho squared plus rho plus 1/4 rho squared d theta hat squared plus sine squared theta hat d phi hat squared, because you've got 1/4 rho squared everywhere. This with a qj, very important, qj, and there's also a qj here. Let me take the qj out the front. I take the qj out the front of this. This becomes d rho squared. This becomes 1/4 rho squared. This becomes 1/4 rho squared. What I've got is that. Now the question is what happens here. You also get plus 1/4 rho squared. But now look at what's coming up. Ooh dear, oh dear. I forgot the important qj. Remember, curl of A is the gradient of V. So whatever I have here is going to be proportional to qj. And so there's an important qj missing here. So when I pull out the qj out the front, I get a 1/qj squared, which I take inside here, and you see that it becomes qj to the minus 1 d psi plus cosine theta hat d phi hat squared. So first and foremost, this metric ain't singular. It's perfectly well behaved as rho goes to 0. But I claim that it is almost flat space. Almost exactly flat space. Now I need more chalk. Well, it's almost flat space. Suppose in the notes I've left an exercise which I encourage you to do. Take complex coordinates, which are, let's see, cosine theta hat over 2, e to the I chi minus, let's say, phi hat, put some hats on it, divided by 2. Zeta 2 is equal to sine theta hat over 2, e to the I chi plus phi hat over 2, with a rho in front, Then if you calculate the flat metric, that's d zeta 2, that's the exercise, you'll find that it's almost exactly this. It is d rho squared plus the quarters come from the fact I've got lots of half angles, d theta hat squared plus sine squared theta hat d phi hat squared. But there's a slight difference here. 1/4 d chi plus cosine theta hat d phi hat squared. Now, so this metric is almost exactly R4 except for this q to the minus 1. So chi is to be identified with qj to the minus 1 psi. And now you've got a metric which is locally perfectly flat. It is R4. So what does this mean? Well, remember, psi is identified with a period of 4 pi. So chi must be the same as chi plus 4 pi divided by qj. Now, if you look at this coverage, you'll see that for R4, you must have 0 is less than chi is less than 4 pi. That would be the right range for chi. It's because of it's 4 pi because of all the half angles. So R4 is the full range of chi from 0 to 4 pi, but what you've got is chi identified with 4 pi mod qj. So therefore, this metric is not exactly R4. This metric is R4 modded out by zqj. I'm sorry, R4 modded out by zqj. Modded out in the sense that this fiber, this angular coordinate, is taken to have a period which is not the natural one for R4, but one that's divided by zq. Good? Not jumping in, Monica? Happy? Okay. Right. So, in other words, the metric is perfectly regular. It's almost perfectly R4, except it's R4 modded up by possibly a discrete subgroup, zqj, depending on the Gibbons-Hawking charge at that point. If qj is 1 or minus 1, it's flat space. If it's 0, it makes no sense because there's no such point. But basically, this is the manifold. It's a lovely manifold. So, at these points, these Gibbons-Hawking points, this metric is perfectly smooth. Now, another factoid about this thing is the asymptotics. I chose the asymptotics the way I did for a good reason. V, remember, is the sum over j of qj over rj, And as r goes to infinity, this goes like q naught over rj, where q naught is the sum of all the qj's. Okay? And so therefore it's asymptotically flat, or asymptotic to, not R4, but it's asymptotic to R4 modded out by ZQ0. In other words, when you go to infinity, it does go to a beautifully flat space, but the period of psi, or chi, sorry, the period of the flat space is modded out by ZQ0. Okay? Questions or comments? So that's why it's called asymptotically locally Euclidean. It's not asymptotic Euclidean, not asymptotic R4, it's asymptotic R4 locally, modulo these identifications. Sorry, yeah, no.
So this is tabulating.
Sorry?
I guess you're hiding a codimension 2 source. So this deficit angle is supposed to happen.
So it's what?
This deficit angle type of singularity, they should happen when you have codimension 2 sources. So these are electric. These are electric sources for.
There's no. Let's see. I mean, you can think of these as what is it? KK monopoles in a sense. They are exactly that. If you take 10-dimensional string theory and compactify on this, these are KK monopoles. But at the moment, they're just beautifully smooth metric.
You can blow up the singularity, so you can blow up the singularity. I mean, it's just like when you have 2 d6 branes, for example, they give you like a d2 singularity. But you can separate the d6 a bit and then get a top-knot space which has 2 centers.
Well, I'm going to go there. I'm going to go there. That's the next thing.
Sense, there's no source, for R4 there's no, I mean, just the d6 center, which is, nothing in it.
Right. So I want to, just before we make a break, I just want to finish on this point. This is R4 mod ZQ. This is why they're called ALE, asymptotically locally Euclidean. And that's why Gibbons and Hawking invented them, and they wanted to find out these guys. Now, the last gasp I want to point out, which is where the danger lies, but where we're going to break through, is remember I said about 15, 20 minutes ago that there are no hyperkähler metrics that are asymptotic to R4 apart from R4 itself. And you can see it very explicitly here. Naively, or not really naively, if you make a Riemannian metric, that means that ds4 squared is positive definite, or positive semi-definite at least. Then you better have V strictly positive. Otherwise, it's going to be horribly singular. That means that when you go to infinity, so Q naught, which is the sum of j of positive numbers. Oh, let me put it that way. That means Qj has to be positive, or 0, of course. But if you want asymptotic to R4, then Q naught had better be 1. And if Q naught, which is the sum of positive numbers, is 1, then the only way to do this is Qj is equal to 1 for some j, some j equals I, and Qj equals 0 otherwise. Which means the whole space is R4. So Gibbons-Hawking metrics aren't an exception to this theorem. The only way to make a Gibbons-Hawking metric that's asymptotic to R4 is have exactly 1 point with charge 1, but that means the space is entirely R4. Well, a priori, we can just do the investigation of ALE spaces, and that's what we're going to do, but we're going to do some magic on this before we're done, and we'll get past this point. But this is a very good time, I think, to break for coffee and rejoin in 10 minutes.
Okay, thank you very much. We're good.
Okay, so we have our hyperkähler geometry, and now our task is to solve the first Dps equation, which is theta is equal to star theta. And as I remarked, because d of theta is 0, because it's a field strength, d star of theta is 0, and so therefore it's harmonic, which means we need topology. And in particular, we need non-trivial elements of H2 of these Gibbons-Hawking spaces And so that's what I've got to do, but before I go there, I'm going to find the non-trivial homology elements that are going to be dual to. I'm looking for the 2 homology of the given talking space. And it's extremely easy to exhibit, and then I'll effectively prove by the time I'm done that it is really cohomological or homological. But to exhibit it, what you should think about is the structure of the given talking space. We have a R3 base, which is these coordinates y. We have ds4 squared, which is equal to v to the minus 1 d psi plus a squared v plus v dy dot dy. And the v's are the sum of qj's over rj's. Rj is equal to y minus yj. Okay, so now, what this means is at above a generic point you have a psi fiber. But you have these given talking points, yj, yi, let's say here, and you have a given talking point here, yj. So, above a generic point, this psi fiber is good and fat. It's a non-trivial thing. But think about what happens when the psi fiber gets above this point. V is blowing up, and psi is blowing down, because v to the minus 1 kills this fiber. So this fiber is coming along happily, but above this point it pinches off. And it also, then it comes fat again, and then pinches off at this fiber, above here. So I claim that you pick any path between here and here, you can make a non-trivial, interesting sphere-like thing by looking at the track of the fiber above the path. And I claim that this, all the homology of this, is exactly in this form. I'm going to define delta ij to be the 2-cycle defined by a path gamma in R3, let's call it gamma, between yi and yj, and of course the psi fiber. As I've depicted here. This is delta ij. Okay. And if you choose a different path, that's just a homotopy equivalence. So therefore those cycles are homotopic, so it just cares about yi and yj. And I claim that's the 2 homology. And in particular, there are half n into n minus 1 choices of these delta ij's. But it turns out, for reasons I'll become clear in a few, perhaps a little bit later, there's a basis, which is basically you put the points in any order, delta I plus 1, and anything else, any other cycle is just a sum of these cycles. And so there are in fact n minus 1 2 cycles. So the beautiful thing about the given talking space is you can literally see the non-trivial 2 cycles. You see them as just where the fibers pinch off. And this is actually a very common way in string theory and other places of actually looking for exactly where the cycles are. You look at you typically wind up with circle or sphere fibrations, and the question is where do they pinch off? And by tracking where they pinch off, you can see the cohomology homology quite explicitly. So there are my cycles. So now I'm going to find the cohomology. What I mean by that is, of course, the thetas that are dual to the homology cycles. And I'll prove that there are n minus 1 of these, and that will in fact prove that there are n minus 1 of those, and that these guys are linearly dependent. Okay, so what am I going to do? First of all, I'm going to simplify things or make things. There's a very canonical set of frames. Half e psi plus a, and then ei plus 1, which is equal to v to the half dyi. Those are the frames that are standard symmetric. Exercise. Show that the spin connection is self-dual in these frames. That's another good exercise. It's in the notes. I digress. All of this to say I want to introduce omega plus, which are going to be a particular set of self-dual two forms. They are E omega I plus, I take E1 wedge EI plus 1 half epsilon ijk EJ plus 1 wedge EK plus 1. So e.g. E1 wedge E2 plus E3 wedge E4 and so forth. These are self-dual by construction in 4 dimensions. Star 4 of omega I is equal to omega I. Well, if you want to take the anti-self-dual ones of those are the hyperkähler forms. I'm not going to get there. But the self-dual ones are the ones I'm interested in. Okay, so I've got some self-dual forms. They form a basis of the things I'm looking for. I'm looking for things where theta is equal to star theta. So they're going to be, in principle, a particular basis of this. So in fact, what I'm going to do is I'm going to write the following expression. Theta I is gradient, actually I should write it, it's the 3-form gradient. It's the gradient in 3 dimensions, so gradient in y, ith component of ki, that carries an index, over v, contracted into omega I. And I think I want a minus sign to get everything to work nicely. Let me just check my notes. I think I've got a plus sign in the notes. Oh, let me just write gradient. I should just write it explicitly. It's equal to dyi, like ddyi of that, times that. I'm going to take that as a ansatz because I know it works. But if you say, let's make this ansatz like that, then I want to keep that. If you impose d theta, you impose this, and if you impose this, you automatically impose that, you find that's equivalent to the Laplacian squared on R3 on ki is equal to 0. So what I've done is I've exhibited for you some interesting 2 forms that are self-dual, and if I choose a harmonic on R3, 2-form harmonic k's, and take this thing, this turns out to be self-dual and closed, and therefore co-closed, and therefore an element of the cohomology. Not quite. I also want to remember to be cohomological, or to make a nice microstate geometry, theta's got to be smooth. So now I want to consider smoothness. Any questions before I go there? So all I've done is I've said, look, this thing's the basis of all self-dual forms. I just wrote it down very explicitly. I could put any set of functions here multiplying vi, but it turns out that this nice gradient of ki over v is a really nice thing to look at because it tells you that it is harmonic provided you wind up with the k being harmonic on the base. Now how do you make it smooth? What you should remember is that v is equal to the sum of qj over rj. And smoothness of theta means that ki over v must be smooth. If this is smooth, theta's smooth, and you're done. But how do you make ki smooth? Well, these things can blow up at points. The ki's can blow up at points. So if I take ki to be equal to the sum over all the given talking points, however many I've got, of some parameters kj, ki sub j over rj, for some kji, any, for the moment, just any real numbers, then this is smooth, because when v is blowing up, on k is blowing up, the singularities cancel, and you get a nice smooth function. So, with this choice, you get smooth thetas.
0 excluded.
Sorry?
Kij should not be 0.
Oh, no, it should not be. No, it can be 0, because when v blows up, this goes to 0.
Ah, okay.
So, in fact, got it? So let me not worry about this index I for the moment. The class of k's I want to think about are these guys. The k's I want to think about are things which are generically summed kj over rj summed over j. How many of them are there? Well, the other thing I want to notice is that if I take k and I replace it by k plus any amount of v, then the corresponding theta is trivial, because you get d derivative of 1. And in fact, you can shift it by any amount, c times v, and that produces, this is called a gauge transformation in this game. And it's called a gauge transformation because it changes the function k but does nothing to the physical solution, because the physical solution doesn't care about the addition of a constant after you've differentiated it. So in particular, this means that if you count the parameters, what am I going to do with this? I need more board space. Let me get rid of that. I'll get rid of that too. Okay, so that means that you have how many parameters here? You have n parameters. But you have one gauge transformation, so -1, which means there are n minus 1 non-trivial cohomological thetas. So it's as simple as that. This is why Gibbons Hawking is such a nice geometry. You can write everything you want as explicitly as you want in terms of harmonic functions on R3. Okay, so I've got that. So now we've got the cohomology we want. Let me make one last little observation, an exercise. Remember I said that the thetas exercise, thetas have a potential, they're d of bi's, and the bi's are very simple. They are ki over v times d psi plus a plus something plus xi I, and the equation you have to solve where xi I is given by, it's a minus the gradient of ki. Exercise, check that this is indeed a potential for that. Okay, so I've got some very nice, yeah, sorry.
You said some i's, you meant ki, ki, ki.
Yeah, okay, yes, I've got this I runs from 1 to 3. And I'm suppressing it for the moment because I don't want to worry about separate different U1s. But indeed, the actual number of these things in each capital I channel, if you like, is n minus 1.
And the C may depend on I.
Yes, indeed.
In their
exactly.
scale.
Yes, I did this more carefully in my notes, but yes. So all this to say is that you a priori have n possible choices of these parameters, but really physically there are only n minus 1 free parameters because there's a trivial transformation. Okay, now, using this fact, a little exercise, which I'll also put in the notes. If you dig around in some of Joseph's and my review articles, you'll find the exercise done for you. But here's the exercise. I claim that this is the homology, and this is the cohomology, and they have to be dual to each other. So that means you should be able to integrate one over the other, and of course you can. And the exercise is to calculate those so-called period integrals, and I'll call them the fluxes of the ith pi ij, which is going to be defined to be the integral of over 4 pi, normalized by 4 pi, the integral over the cycle I call delta ij, this guy, of theta I. So, cohomological flux integrated over a 2 cycle. The exercise is to show that it is kj over qj minus ki over qi. And it's very easy. So let me just give you a hint as to how to do the exercise. If you cut off the endpoints, then this is a perfectly good potential. Therefore, you can integrate it. You can do this integral trivially by writing this as the integral of dbi. And the only problem you have is to pick up the residues at the endpoints. And the residues at the endpoints are given by the value of k over v at the endpoints, which is this and this. That's where they come from. And so now you can see very explicitly that if you're measuring and calculating all the periods over all base points, it only turns out to be differences of kj over qj, which makes the this obviously being a dimension n space, dimension n minus 1 space. Because the only residues are the k's over the q's, and then you only get differences. So I've proven in one fell swoop, first of all, this is certainly homology, and this is certainly cohomology, because I've got non-zero period integrals. And moreover, I've shown that the basis is n minus 1 dimensional. So we have our cohomology. We have our non-trivial topological fluxes. Okay, so we got Dps equation 1 done. We have we have now 4 harmonic functions. Governing the solution, we'll have 8 by the time we're done. The first harmonic function is the given talking function. And now we have 3 more, the 3 k's of Rj. And these are the guys that build the thetas. So we've explicitly made the cohomology. Everybody happy? Good. Okay. Looking puzzled, Marianne. You good? Good?
I'm wondering, the K's are quantized or not?
Ah, okay. I'm ignoring all those. There are some things that sacrifice. Technically, yes, all these k's are quantized because you have to, it's the usual direct quantization.
The difference between them is quantized.
Yes, okay. The difference is quantized. Actually, the difference of these is quantized, I think. And the q's are quantized, so therefore, yes. They're magnetic monopoles, so they have the same quantization conditions as a magnetic monopole. So I said they're in R, but really they're in Z with the appropriate lattice scaling. So, yeah, there was a factor of Z2 a factor of 2 we never quite got straight. If you want to see the details, there's another paper by Berglund. It's referenced in the notes, Berglund and Shimon and Levy, thank you. It's referenced in the notes where they actually do the quantization. Okay, so now, next step, Dps equation 2. And this turns out to be dead easy. Dps equation 2 says that the del squareds of the zi's are given by the star of theta j wedge theta k with aCijk and a factor of 2. So it's a very straightforward exercise, but let me show you sort of the elements. You now put in what these thetas are. Remember, thetas are simply given by the gradients A of ki over v times these omegas. And the omegas were chosen so omega wedge omega is the volume form, so the dual of omegas is quite trivial. And so you see that this source really boils down to something like dA of ki over v, kj over v, and another dA, same dkk over v. That's the right-hand side. And it's elementary to integrate. You find that Zi has a particular solution that is nothing other thanCijk, probably with a half, kj over times kk over v. It is automatically satisfied by that. So it's trivial to do this next equation. Let me just check I've got the factors of 2 right, with a half. Indeed. But remember, it's a harmonic equation. So there are in principle some other functions, Li, which we have to add, and these Li's are going to be part of the list of harmonic functions. Li's can in principle be harmonic. And in fact on R4, on the full manifold, but let's just make it an R3, is equal to 0. So there's the solution to BPS2. It's completely trivial. You just differentiate like crazy with the Laplacian, use the fact that k's and v's are all harmonic, so whenever 2 derivatives wind up on any one of these things, they go away, and what's left is in fact exactly the source term I was muttering about. Okay, so BPS2 is easy, but there's another issue. I did this in a different order in the notes, but I think it's natural to talk about it here. Remember, for microstate geometries, our goal is to make everything smooth. And remember, if you put theta to 0, this term, sorry, yeah.
So these possible shifts in LIs,
Yes?
these have nothing to do with the gauge freedom that you had before of
No.
shifting
No,
K?
this is real physical
It's
stuff.
independent.
Yeah, but if you do the shift, K goes to K of V, then it'll shift L by something, a multiple of V. So you can shift it. There will be a gauge knock-on
So
effect.
I was wondering maybe the LIs have the shape of precisely the
I'm going to fix it. I'm going to exactly fix the LIs for you in a minute.
Okay.
Totally fix them. So, but indeed, if you do a gauge transformation here, it will spit out a term that gets absorbed into here because you shift K by V, it cancels the V in the bottom, and you're left with K, so it shifts L by K, excuse me. Yeah, so exactly, there is a gauge knock-on effect. Okay, so remember the structure. If you put the thetas to 0, then basically I mentioned there was an equation del squared Zi is equal to 0, and I said that's black holes, or in fact black rings. So this is the capacity in principle to add black holes and black rings. Doesn't mean you want to set it to 0. The goal, remember, is a smooth geometry. And that means, and remember the Zi's, for example, Z1, Z2, Z3, to the third is one of the metric functions. And I didn't talk about it here, but it's in the notes. The xi's are related to z's in interesting ways. They are the form z over zi. Things like this. So, all this to say is that the z's need to be smooth. So in particular, what we're going to do is we look at what happens as Rj goes to 0, when you approach the given talking points. And so if you look at this, you see there's a first term which is 1/2 Cijk. I'm just going to take the lead, well, it's the only singular piece. There's a Kj, a Kk, and then over the given talking point gate over Qj, and you have a 1 over R squared from the top and a 1 over R on the bottom times 1 over Rj. That looks singular. It is singular. But you fix it. And the way you fix it is by picking L. And so you achieve your goal by simply saying the Li is going to be a harmonic function. I'm going to put a 1 in it for reasons I'll explain in a second. And then there's going to be a sum of Li whatever, over Rj, and this tells me what to do. Lii must be equal to Cijk with a factor of 1/2 and a minus sign, Kj Kk I over Qj. Qi. And the whole point is that this is exactly configured to cancel this singularity in the first term. And if you do that, the Zi's are smooth. If you do anything else, the Zi's will have a singularity and you'll have a black object in your solution. It'll be a black ring generically. But so if you want to make black rings and microstate geometries, you just choose some singular sources for this. But our goal here is microstate geometry, so everything in sight I want to make smooth.
I don't understand. You sum over what in Li?
J and K.
No, they are the Li, capital L.
This is capital Li.
Yeah.
Yes.
The sum you
J equals 1 to n over all the given talking points.
Okay, and Li is constant.
Yep.
Lii.
Yeah,
is
they're
constant
all
for
constants.
J. Okay.
But the constants are fixed in terms of the magnetic fluxes. Every one of these constants is actually now being fixed in terms of the Ks. So a priori.
What there means is that L has a different index I with respect to as compared to the coordinate Rj.
Yes. So for each Zi, the capital I's take values 1 to 3. For each of these the electrostatic potentials, there's a 1 I'll come to in a minute, and then there's a charge, which is I at every given talking point. There are 3, and did I make a mistake? Oh, sorry, Lj. I'm sorry. Thank you. Thank you. I'm sorry. Yeah, I'm sorry. Yes. So the whole point is that a priori you've got another harmonic function, but in fact, smoothness of this function requires that every single pole of this is arranged so it cancels the poles of this. So the magnetic flux. So in fact, what we're going to find is once you've picked the magnetic fluxes, smoothness fixes the entire rest of the solution. So, another ones. Why did I do that? Because I want the zi's to go to 1 at infinity. You can let them go to any other constant you like, but remember the warp factors and all those things in front of the metric, I just want them to go. It means that ddt it goes to minus t squared and infinity and all these things. So this is just a normalization of the asymptotic structure of the metric. Okay. Now, the last gasp of this. So we've now got this layer, but most particularly, we have found that zi's are now completely fixed. But we've now got some new harmonic functions. I'll make sure I don't screw up. J equals 1 to n. And the LJs are fixed entirely in terms of these guys. J, 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 J. There's no freedom. Okay, so now we go to the last gasp. We've got the Z's, and now we go to the last layer of the Dps equations. Dk plus star dk is equal to zi theta I. We have to solve this. It turns out it's equally, well, it's a little bit more technical, but it's basically straightforward. So what do? This is a 1 form. So you make an ansatz for it. And the way you make the ansatz is the following. You say k is going to be equal to something parallel to the fiber, which I'm going to call the function mu, and something which is on R3. So you decompose along the fiber and along the base. Also along the R3. And then you just simply shove it all in. You've got everything here, you know everything here, and now you just write down this equation. It gets a bit of a nightmare. And I'll write down maybe one of the equations, but it's not trivial, but it's very, very straightforward. So let me actually write down what you get. Cheat a little bit. Never remember this part. So, what actually happens is that you find that you can write it the following way. Del cross omega is equal to V grad mu minus mu grad V minus V sum I equals 1 to 3. Repeated indices of sum, but I'm just being very explicit. Grad ki over v. It becomes that. And you see that this is nothing other than basically, this is what comes from zi theta I. And this is the d operator hitting the mu and the d psi plus a. It's exactly that equation. So simple fact is you take the divergence of this equation, take dev dot of this vanishes, then basically when it hits here, it vanishes. When it hits here, it cancels against when it hits here. And what you wind up with is del squared mu on R3 is equal to the divergence of this pile of horror. You write it out, and it turns out, I've got the mu. You write it out, and it turns out it has a very explicit solution. Mu is equal to K1, K2, K3, all three of them over V squared, plus a half KI Li, and that exactly solves that equation. And then you have the freedom to add another harmonic function. M is going to be harmonic. It turns out that this is del squared of m is 0. So it's completely trivial to solve that. And then this equation, once you put that solution back in, this equation collapses to something kind of nice, which is equal to V grad m minus m grad v plus 1/2 ki, I may have this the wrong way around, ki grad li minus li grad ki. It might be the other way around, so there's a plus or minus. The correct answer's in the notes. Okay, so here is explicitly the value of mu written out up to another harmonic function. That's the 8th harmonic function. But if you look at the last equation you have to solve, and you take the divergence of this, then either you get cancellation between here and here, or you get del squared on m, or you get del squared on v. So the fact that every one of these functions is a harmonic means that that equation is explicitly solvable. So this is the integrability of that equation. The technical morass in this game is actually getting the detailed solution of this, but if you've only got 2 or 3 given talking points, it's quite easy. If you've got more, it gets a bit of a mess. But anyway, we've now got the last part of the solution, which is this, and then there's a vector field that goes along for the ride, which basically, if you understand this, it turns out you understand everything you need to know about that. And then the last gasp, what about this function m? It's exactly the same deal. Smoothness. Smoothness requires that our function, this k that I've written down here, better be smooth. Smoothness. Mu must be smooth. Okay, so what does that mean? In particular, when you go from Rj goes to 0, if you look at this, there's a dangerous singularity because this has got 3 poles, this has only got 2. Similarly, this has got 2, oops, over V. This has got 2 poles, that's only got 1. So in particular, there's going to be a term which is in the form of K1, K2, K3, 3 over Qj squared from the first thing. This is going to produce a K times, well, this was K2, K3. So this is also going to produce another exactly the same coefficient here. And then you're going to have M is going to be, now I'm going to keep it constant. This is important. Sum J equals 1 to M of Mj over Rj. Same harmonic source. And I've got a singular term that's proportional to this. So in fact, hardly surprisingly, smoothness requires Mj is equal to, what is it? Lost it. Mj is equal to, I'm getting ahead of myself, but I think it's useful to do it here. Mj is, where's it gone? 1/2. And that means that then mu is smooth. And the basic point is, the dangerous point is, as I said, when Rj goes to 0, and this produces a pole of exactly that type. If you use the explicit form for Li's, remember the Li's are 1/2 Cijk of, with a minus sign, of Kj Kk over Qj J. And when you contract that with the third k, it produces exactly a contribution of this type. And you add them all up, and you find to cancel them all, you've got to put the ends like that. The last gasp is this constant. Mu, remember, is part of the angular momentum vector. And you would like to go to a non-rotating frame at infinity, which means the angular momentum needs to die at infinity. And that fixes m0. And m0 then gets fixed in an interesting way, minus 1/2 Q0 to the minus 1 of the sum over everybody. Sum I equals 1 to 3, and the sum j equals 1 to n of kji. So basically, if you want it to not rotate at infinity, you have to kill it off, and that's what the role of m0 is. So, all of this to say, let me recap what we did. And then this gets solved, and there's a whole story about Dirac strings here, which I'm going to ignore because I don't have time, but I put a bit more about it in the notes. So let me recap what we did. we started with the Gibbons-Hawking base, which is started with R3 with a fiber over it, a psi fiber. And then this is encoded in, all the details are encoded in a single harmonic function over Rj. We then introduced fluxes, which were encoded sum over j of some ki j over Rj. And then we set about solving the rest of the details, the electrostatic potentials. And we found they were given by Cijk, a half kj kk over v plus li. But this was entirely fixed in terms of k's. Love the k's. And then the last class was we then worked out the last part of the metric, the angular momentum vector, mu d psi plus a. And this was given by k1, k2, k3 over v squared plus a half ki li over v plus m. And this was also fixed in terms of the k's. So in other words, everything is determined by the geometry of the base and the magnetic fluxes and smoothness. Every other aspect of this solution is fixed rigidly once you've decided where the points are, what the charges are, and what the magnetic fluxes are. Everything is fixed. But everything can be explicitly solved and explicitly analyzed, and this is a genuine microstate geometry. Okay, so I've got 20 minutes left. Which way am I going to jump? Pause momentarily for questions, perhaps, for openness. Okay, I'm not going to talk about direct strings. There's a little bit about it in notes, but I'm going to say more about that if there's questions later. Right, now, at the moment we've got a smooth geometry, but there's some things hidden. Perhaps I've got two ways to go at this point. Bubble equations or ambipolar. Yeah, I'll go ambipolar, that's more fun. Any questions before I do this? We're going to have to worry about closed time-like curves, and I'm going to probably start with that next time, or maybe I'll make a start on it this time. I've made everything in sight smooth, but I haven't necessarily guaranteed the metric is well behaved. In particular, there might be closed time-like curves, and I've got to fix that and discuss that, so that's a more technical discussion. But what I want to do is actually talk about the thing that gets you past that roadblock I mentioned last time. And it involves something called ambipolar geometries. Okay. So this is the slightly radical divergence from Gibbons-Hawking. Any questions before I go here, though? So this is the basic setup. We have a completely, we can go ahead and take our favorite Gibbons-Hawking space and calculate. But first of all, remember I said, if you do standard Gibbons-Hawking spaces, you're not going to get asymptotically R4. You're going to get ALE spaces, things that are R4 modded by discrete groups. I don't want that. And second, it turns out that if you do it in Gibbons-Hawking spaces, just by themselves, you'll find that the solutions you get are basically full of closed time-like curves. So now I'm going to pull a trick, a rabbit out of the hat. And this is something that was a sort of insight that came from a paper of Justo and Mathur, and then Joseph and I mined the hell out of it to get the most interesting microstate geometries there are. Okay, so all I'm going to do now is just take everything I've just done and generalize the hell out of it in a very, very simple way, because we've got all the formulae we need. So basically, so far, I've been saying DS4, well, this is some Riemannian hyperkähler base. Okay. And that's the sort of natural thing, and if you look at Gutowski and Gauntlets and all these other people who are classifying the Dps equations for the system, that's what they do, and it's perfectly reasonable to do. But let me point out there's something quite radical you can do. Suppose you allow something bizarre. ds4 squared to change from signature +4 to -4. Which means you allow it to change sign. Overall sign. In other words, you don't require it to be positive definite. Looks like it's crazy, but if Z changes sign at exactly the same place, then ds5 could potentially be smooth and Riemannian. Sorry, smooth and Lorentzian. So the rabbit out of the hat is to do something that seems on the face of insane. You have these warp factors in the metric, but if you allow this metric to do something wild and crazy and be terribly singular by changing sign, you might be able to repair it by making this change sign. You won't screw up because it appears as a square here. This is called ambipolar. It means that you have the metric can be positive definite in one region and negative definite in another region, with a zone between, which we'll talk about next time, where Z momentarily vanishes, sorry, V momentarily vanishes. If you look at it in terms of the Gibbons-Hawking space, let's take what it means for the Gibbons-Hawking space. What we have for Gibbons-Hawking is ds squared is equal to v to the -1 d psi plus a squared plus v times dy dot dy. What this means for Gibbons-Hawking is we're going to allow it to change sign. V to change sign. And before, Riemannian, or positive definite, meant that Qj was strictly positive or 0. We're going to abandon that, and we're going to allow Qj to be an element of the integers, positive or negative. And this means that if you get near a negative charge, V is negative, and if you get near a positive charge, V is positive. And then there are points where V is 0. That can cause all sorts of chaos in the metric. But remember, ds5 squared is the thing we're shooting for. The goal is that ds5 squared is required to be smooth and Lorentzian. And ds4 can be anything that it needs to be in the service of making this smooth and Lorentzian. So, in fact, it was the paper of Justo and Mathur that found one example, which was just bizarre, that there was a change of signature in the metric. And then we realized it was a thing that we could just do hugely. So that's what we're going to do. So what I want to do and spend the last 15 minutes or so is talk about why or how this actually works. Because it looks really bad. Singular here, V is 0, it's degenerate there. The inverse metric looks like hell. But it all works. And in fact, if you do it right, everything can be made as smooth as you like, and this is where you get the vast number of microstate geometries that are interesting. So let's set about looking at what happens. At least make it plausible. Any questions then before I proceed? So my claim is that V doesn't have to be positive definite. It can change sign. And in fact, generically, you can accept any hypercalometric whose signature goes from +4 to -4. So let's look at it. Z. Remember what Z is? Z is Z1, Z2, Z3 to the third. And that goes like K. Let me just put it like this. Remember the Z's. Zi goes like Kj, Kk over V. So if you look at this, this goes like 1 over V, near V is 0. Because you get 1 over V here, 1 over V here, and 1 over V there, so you get the cube root of 1 over V. Okay, so look at this metric, ds5 squared, then near v equals 0, ds5 squared contains a piece which is ds5 squared, which is going to be equal to minus v squared, goes like minus v squared, yes, goes like v squared d psi dt plus k squared. Okay, fair enough. But now this piece goes like plus, and then you get this 1 over v term with a constant on top, times the Gibbons Hawking metric, v to the minus 1 d psi plus a plus v dy dot dy. Okay. So the first thing you notice is the good bit, the easy good bit. The easy good bit is that this 1 over v cancels this v, and in that R3 direction, everything's perfect. So it's positive definite here. So 3 out of 5 directions are working properly. Now, this looks really, really bad. U squared. Here you have a v to the minus 2 d psi plus a squared. So it looks when you hit these v equals 0 surfaces like all sorts of terrible things are going to happen. But this term comes and saves you. So, the first thing you do now is you've got to look at the last spatial direction and ask whether everything is good. And I highly recommend this as an exercise. I'm going to tell you the answer. So remember, let's just count powers of v. K contains a, we're going to look in the direction d psi plus a. And think about it. We've already got a problem term here. So there's some number 1 over v squared d psi plus a coming from this part of the metric. But there's something coming from here. It is minus v squared mu squared d psi plus a squared from this term. Now, remember, mu starts off with a term k over v squared. So this term contains a piece which is v squared k over v to the 4th, sorry, squared, because it's mu squared. And lo and behold, it's v squared times v to the 4th, and this is v squared. They're exactly the same term. And so there's perfect cancellation at order 1 over v squared. There is also perfect cancellation at order 1 over v. So the exercise, and I'm going to write down the answer, it's fairly tedious, but it's instructive, is the following. Where's it gone? There it is. Okay. That the coefficient of d psi plus a squared is proportional to something which is basically what we call q d psi plus a squared, and q is equal to, and it's a terrible long thing, minus m squared v squared plus m a third minus a third m, this is in the notes, cijk ki kj kk plus minus mv ki li. I'm not going to keep going, there's a lot of terms. The important point is it's quartic in every single harmonic function and contains no 1 over v's. So in other words, the metric is beautifully regular, and what is happening is that the minus, whatever it is, there's a minus z to the minus 2 k squared plus the z times v d psi plus a squared coming from there. There's a fantastic conspiracy between that and that. This term coming from here and this term coming from the metric, such that all singularities at v equals 0 surface cancel. So you've got a nice positive definite metric on the space. Okay. Perhaps the best way of illustrating this is to show you that nothing goes wrong with the Maxwell field. So let me look at the Maxwell field. The metric is a bit of a bear. The Maxwell field is much clearer to see what's going on. So everything looks horrible when you write down my Maxwell field decomposition. So remember what I did? I said AI is equal to minus, also plus Zi to the minus 1 dt plus k plus bi and dbi and bi is equal to k over v d psi plus a plus xi I. That's ki. And xi I has the property that the curl of xi I is equal to minus the gradient of k. So this part's fine. But look, here's the horrible thing. When v goes to 0, this magnetic flux is going through the roof, and theta is even worse. It's got the derivative of this thing. So this thing's horribly singular at v equals 0. What rescues you is this. How does it come about? Zi, let's just do 1, A1. This is Z1, and this is B1. So Z1 to the minus 1. Well, Z1 contains a piece which is K2, K3 over V. So when you multiply it, and then K contains a piece which is mu, which is K1, K2, K3 over V squared. And I'm only going to care about the one at the most divergent pieces. So look what happens. This thing contains a piece which is horrible. It's the K1 over V times d psi plus A. That's blowing up. But look at the d psi plus A piece that's coming from here. It's got a piece which is times d psi plus A, like this, but it's being multiplied by this guy, inverted. So that's V over K2, it's K3, and there's a minus sign then. And so look what happens. The K3 cancels the K3, the K2 cancels the K2, this power cancels that power, and you get K1 over V, which cancels that K1 over V. So amazingly, what's happening is the individual pieces are terribly singular at the v equals 0 surface, but when you assemble it into the final solution, it's beautifully smooth at the v equals 0 surfaces. Okay, so let me add to the exercises. In ambipolar spaces, the last exercise I gave you about fluxes, well, in ambipolar is crap. Theta I, remember, is equal to dB I, which is terribly singular. And I said prove that 1 over 4 pi of the integral of theta I over this cycle, delta I, delta j, is equal to kj I over qj minus ki. And this is all well and good if you, ki is I, if you are on an ordinary given talking, but on ambipolar, this is terrible because theta is blowing up on a v equals 0 surface. However, the message I just gave should be very clear. You don't take the pieces. You take Fi, which is equal to dBi, that's the magnetic piece, minus d of Zi, that's minus that plus that, minus 1 dt plus k. And the exercise is to prove that this is exactly correct if you replace this with Fi. In other words, if you assemble the full physical field, which is smooth, where the piece of this cancels the singular piece of this, you can integrate it across any of these damn cycles, and you will get the same period. So I was using a convenient basis before where I could separate off what I call the magnetic piece. But there's a critical piece here which makes it smooth, but this period is the same. So long, but this is true so long as mu at rj equals 0 is 0. And I'm going to say a lot more about that next time, perhaps. You have to have this. So in other words, ambipolar is this surreal fact that you can allow the metric to change sign, and you can do it in a really, really nice way.
Sorry.
Yeah.
Can we just step back a little bit?
Sure.
So instead of you had B that was blowing up, and
Yep.
then you compensate with the next exact,
Yep,
well,
but
with the
that-
other term, and then you take the,
Yep.
the flux.
Remember, the full five-dimensional field is not just B, it's Bi, the magnetic piece, with a potential, I think it was minus actually if I did the conventions right. That's the full electromagnetic field.
Okay, so now you're saying with this new contribution, everything is smooth?
Yep.
Okay, and now you plug in this flux that is the stereo derivative, but now you remove all singularities with these two contributions.
Yes.
And you're saying that you're taking the stereo derivative from some two cycles, so this is basically a two-sphere.
This one, yeah, exactly the same integral as before.
And the period
Yes.
of some exact form is giving you something that
Oh, not an exact form. B is only a local potential. It's the usual story like the monopole. So, you know, if I give you the standard monopole, F is equal to sine theta d theta d phi, then you're used to saying, well, A is equal to cosine. No, but if you, let me just finish. Cosine d phi, that's only a local potential, but this has a non-trivial period over a two-sphere.
Okay.
Yeah, no, this is local. This is a local potential. Because these are local magnetic fluxes, so B is only locally defined on the sphere.
Sure.
That's part of the exercise of calculating the flux. You have to understand that in very great detail to calculate these fluxes. But what I'm saying is that previously I could extract the magnetic pieces and not pay and calculate the fluxes. The magnetic pieces are terribly singular at these V equals 0 surfaces. But if I combine it to the full Maxwell field, it's no longer singular, and that full Maxwell field has the same period. Modulo this constraint, which looks mysterious, which I'll come back to. Let me explain where that constraint's coming from, and then we'll probably finish there. And I will talk about an example of this next time. So I'll explain what we bought by doing this. Let me finish. So let me say where this funny constraint comes from, at least in terms of the geometry. Remember, we have an R3, and we've got these Gibbons-Hawking points. And remember, the whole discussion was that there's a potential V in ds squared is equal, let me write it down to the five-dimensional metric in explicit and gory detail. ds5 squared is equal to z to the minus 2 dt, and I'm going to write down what k is. It's mu d psi plus a squared plus omega all squared plus z squared, and I'm going to write down this in gory detail, v to the minus 1 d psi plus a squared plus v dy. And so in the Gibbons-Hawking base, when v blows up, the cycle blows down. So you have these big fat circles which then pinch off above the Gibbons-Hawking points, and here are your homology spheres. So now the question is, can this get screwed up by the total geometry? So this psi circle is pinching off beautifully. Now remember, I made z smooth, so therefore z goes to finite as rj goes to 0. So therefore this doesn't change anything. This doesn't change anything, but look in here. What can happen as you go near rj goes to 0 is that mu j goes to finite, mu goes to finite. Then you're in trouble, because the sphere, this circle, now has finite size. So this constraint is required to make sure that the pinching off still happens. And so to make sure you still have homology cycles in the full five-dimensional metric, you have to require this. But also, it's even worse. You have to require this for another reason. This circle, if mu j goes to a finite value, is a closed time-like curve. It's got a minus sign. It says that that curve is a time-like trajectory. So you must require this, and this is the CTC analysis, which I'm going to talk about next time. But just from the point of view of geometry, you can see that it's required that this vanish so that the cycle is still a cycle. If this were finite, this circle would not blow down. It would just be some horrible, piece of continuing U1 vibration. So to get the cycle to pinch off and actually be there, you have to have mu go to 0. And if you do the integrals, you'll also see that you only get a sensible result if the mu's vanish. Okay, so let me summarize and finish. So what did we just buy? We realized that there's a whole new world out there of hyperkähler, ambipolar hyperkähler geometries, which I've been trying to get, years ago I've been trying to get mathematicians interested in for a long time. And finally, I think Nigel Hitchin's beginning to nibble at the bait. So, physically, there's a whole class of hyperkähler manifolds, ambipolar, things that change signature. And they create huge numbers of, it turns out, microstate geometries. And in fact, they can generate large numbers of these things. They actually seem to be more generic. And so the V, given Hawking potential, should be allowed to have all these properties. Qj is now an element of Z. And if you want asymptotic to R4, then the quantity Q0, which is the sum of the Qj's, should be put to 1. And that's easily realized, because you're allowed plus 1s and minus 1s. Moreover, you can take Qj's, if you want to make them just magnitude plus or minus 1, everywhere. And then there are no orbifold singularities either. So the interesting, completely smooth, without any orbifold singularities, is a sprinkling of plus 1s and minus 1s, with one more plus 1 than there is minus 1, and that's asymptotic to R4. So this gives you the ability to go way beyond the sort of standard Gibbons-Hawking ALE space. You now have asymptotically R4 spaces. You can throw things on bubbles. And I'll start next time by talking about what happens when you take the simplest such geometry, which is where you take the Gibbons-Hawking potential 1 over R plus minus 1 over R minus. If you just do this construction, you wind up with a beautifully smooth space-time. And we'll talk about that next time. I think I should stop here.
We have time for questions.
No.
Everyone is clear? Okay. And next slide.
You're welcome. Thank you. Got rid of it.